So hi and welcome back, and this is the second video that I have that discusses about uniform circular motion in a horizontal axis. Okay, horizontal uniform circular motion. So first one that we discuss is about the disk and a coin on a surface or an object on a rotating disk. This problem that we're going to be encountering right now is something to do about conical pendulum. So it goes in circle. So just like this illustration right here, where we have a, uh, a a ball based on this problem. It's actually a round object with a mass m, uppercase M, and it's connected to a string with a length L, and it forms an angle. Okay, so it forms an angle, and we all know why we cannot have a perfect 90-degree over here, because if that's the case, okay, so if that's the case, then one of the function will be 0, which is your sine function. Is it sine? Sine of 90? Yeah, sine of 90 is 0. So therefore, there's no tension along our horizontal. Okay. So that's the reason why we cannot have 90. Instead, we have a measurement of an angle, but the angle is not really that much. It's only a small angle. Okay, so the faster it goes, what will happen, this one will open up more. The slower it goes, this one will become closer, making our radius a little bit what we call shorter. Okay, so shorter radius. Now reading this problem, it says that a ball M connected to a string of length L. A student holding a free end of the string whirls the ball in a horizontal circle, just like what I mentioned, with constant speed. Okay, constant velocity. The angle between the string and the velocity and the vertical is theta. The student attempts to whirl the ball as fast and faster in order to make the string become horizontal. No matter how fast the student whirls the ball, okay, the string is never exactly horizontal. Those kind of questions might come up. Maybe there will be another video that I will upload that will explain to you and show you the solution to why we cannot have a perfect horizontal line on a conical pendulum. So at this point, if you notice that the angle is measured along the vertical axis, so vertical axis right here. So if I am going to draw our imaginary x and y coordinates along the ball, if this is our x and this is our y, you notice that this angle right here is the same measurement right here. So that's theta is also your theta right here. So it means that this angle is measured along vertical. Okay, so this angle is measured along vertical. So therefore, what are the forces acting if we are going to draw our free body diagram? First of all, because we are on the surface of the earth, then we have our force of gravity. The next force, we don't have normal force, but it is a string, so therefore this string will basically create or produce force that is strong enough to carry our mass. So this is our tension. Well, sometimes we can use Ft, but the issue with Ft is that when we have the x and y, so you have F subscript T subscript X, F subscript T and X or Y, then there's too many subscript. That is so sometimes it is hard to keep track of. So that's why we're just going to use T instead. So first question is determine the tension exerted on the string. Okay, so letter B. Let's solve for the tension on the string. Now, why don't we redraw our free body diagram somewhere here as part of our solution? So if I have my FG, and FG is simply mass times G and F. Why am I using uppercase M? Because the problem states it's uppercase M. And now we have our tension, which is right here, tension. And this one produces an, or projects an angle, which is right here. Let's draw those dotted lines and then dotted lines for our X. So therefore, if this is angle theta, this is tangent tension X, and this one is our Y component for our tension. Since it's measured along the x-axis or measured along the y-axis, so therefore the functions that we're going to be using is as follows to represent the x. So I'm looking for my green pen. Can't find my green pen. Let's use the blue one. So we can say that tension x and tension y is simply equivalent to the tension itself multiplied by the function. Since the angle is measured from the vertical axis, so y will turn out to be cosine theta, while x is going to be a function of sine theta. Now, just like what I mentioned in the previous video about horizontal circle or circular motion, we will assume that forces along the y-axis is always balanced, or there's no change in acceleration or change in the state of motion. So we can say that the summation of forces along the y-axis for our case here is simply equivalent to 0, while since the motion is on a horizontal axis, rotating axis, or the rotation of axis is along the horizontal axis, so therefore along the x-axis is simply equivalent to mass multiplied by the centripetal acceleration. Okay. So these are some of the conditions that we have established from our previous video. So now if we proceed for B, determine the tension exerted on the string. So what is the tension? So therefore we can actually start by looking at the summation of forces along the y-axis, which is equivalent to 0. Then we can sum up all the forces, where positive going up, negative going down. T sub y is positive minus f of g equals 0. Now we can just move our f of g to the other side of the equation, since they are negative, equal opposite direction, equals a 0, equals fg. Why did I put 0? So that's fg. Okay, so fg. So that's fg. So now we can continue that t sub y is basically t cosine theta is equivalent to mass times g. Since Fg is simply equivalent to mass times g, so now I want to get rid of anything close to our tension in order to get the value of tension by itself. So let's divide both sides by cosine theta. Therefore, I would have an answer for my tension to be mass times the acceleration due to gravity divided by cosine of theta. Go. So step number 1, we were able to solve for our tension. Now let's figure out the acceleration for centripetal acceleration. So let's figure out the centripetal acceleration. Let me just move my video. So for letter B, it's done. So now let's work on letter C. Let's use a different pen so to recognize the difference. So this is letter C. So let us see, what is the centripetal acceleration? Where can we find the centripetal acceleration? Definitely we have it right here. So let us figure out the centripetal acceleration by analyzing the forces acting along the horizontal axis. And since the circular motion happens along the circular axis or along the x-axis, so therefore we will use the centripetal acceleration instead of the linear acceleration. So what are the different forces acting along the x-axis? And that is T of x. T of x equals mass, and in this case our m is uppercase M, multiplied by the centripetal acceleration. Now let's figure out if this is negative or positive. If you notice, the direction is always towards the center. So if I am going to draw using my green pen to represent the centripetal acceleration, then that is towards the center, since it's centripetal, center-seeking direction. Center-seeking direction. Now, we have the same direction as our tension of x, or the x component of our tension. It is towards the center, so therefore we all know that tension x, or the component of the tension at our x-axis, is simply a positive value. Now, I'm more concerned about acceleration, centripetal acceleration. So if I divide both sides by uppercase M, therefore I can have AC equals to T of x over the mass M. But T of x is simply T sine theta, so we can just plug in the value, and that is T times sine theta over M. So we can use this as our equation. But some might say, well, we can still simplify it if we plug in this value, so we can cancel our m's or any other values. Okay, so we can proceed with that if we want to, and for the sake of just showing how will it look like, so why don't we try it? So centripetal acceleration, which is this one, but instead of using t, let's plug in this value right here, which means I will replace my t with mg cosine theta multiplied by sine theta over m, which is our m. Right away, we know what's going to happen. Our m will cancel out, and sine over cosine, so we can have this value over here, which is sine theta over cosine theta times g. And sine theta over cosine theta is simply our tangent function times g. So it's either you have this equation or this value for our centripetal acceleration based on given information in our problem. Okay, so letter D, what is the tangential velocity of the ball? Okay, so what is the tangential velocity? So let's use a different color ink. Let's use, what color I haven't used yet? Let's use the purple one. So letter D, what is the tangential velocity of the ball? So velocity, we can use this equation, which is 2 pi over r over the period. Period t. Please do not get confused by this value of t. This is not t of the tension, okay? But instead, this is period. Now, we can stay away from that if we use a different equation, okay? And that is acceleration is equivalent to v squared over r. So we can use this instead of using this, so we don't get confused by the period t. And besides, you were not given the value of t, or it wasn't mentioned in the problem at all, so we can proceed by using this one. Now, our v sub squared is simply by cross multiplying it, so we have a times a sub c, or the centripetal acceleration multiplied by the radius. But we all know that we cannot, so we don't want our v squared, but instead we want our v, so just take the square root of both sides of the equation, giving us the centripetal acceleration multiplied by the r. Now another thing is that r is not provided. R is not provided, however, we were provided with the length of the string. And if we notice, that's your triangle right here. And that is your theta. So if I want to figure out the r, which is this x component right here, r is simply, what is that function? So that is opposite over hypotenuse, which is sine theta, opposite, which is r, over the length. Now I don't want to solve for my r, but I want to solve for, I don't want to solve for my sine theta, but I wanted to solve for my r, and represents my answer in terms of sine and L. So this means that I have my L multiplied by sine theta. So let us replace this value right here. Square root of AC. Now let's put our AC, which is tangent theta, tangent theta times G multiplied by L sine theta. So that's the square root of all of it. Okay, so if you want to place your parentheses to make sure that they're very organized, so you can place it this way. So that is the velocity of, or the tangential velocity of our conical pendulum, as we call it. So now, last but not least, how can we solve for the value of theta? How can we solve for the value of theta? Letter D. Theta. What's theta? So how can we represent the value of theta? So by looking at this equation right here, okay, so looking at these steps from letter C, okay, so letter C, so we can say from solution of letter C, A of C equals tangent theta times G. So now we can divide both sides by G in order to have, well, or we can reorganize it. I can just say that that is tangent theta. G equals A of C. They're the same. Okay? I'm just replacing their spots. So now I can divide both sides by G. Now I have tangent theta equals the centripetal acceleration over G. Or I'm not concerned about tangent theta, but I'm only concerned about theta. So now I can take the arc tangent of AC, which is the centripetal acceleration over G. So it's basically the ratio of the centripetal acceleration and the acceleration due to gravity. And then you take the arc sine of that ratio. That is your angle. Hope this solution helps you, and see you in the next video.